Good afternoon, good morning, good evening, everybody, and thank you very much for having me. The aim of the paper that I co-authored for this special issue is about additive manufacturing and flexible electronics in the context of Internet of Things. You may wonder why we need additive manufacturing in IoT applications, and the reasons are manifold. Some of them were already mentioned by Professor Tenzeris. 3D printing allows us to use new materials, which have specific features that are suitable for our applications. It allows us to develop new shapes that can enhance our sensors. It improves the integrability with the objects that we want to monitor with IoT nodes. And most of all, it allows us to reduce the environmental footprint of electronics. And this is very much needed because in the future, we want to have billions of these IoT nodes distributed in the environment. However, to make these 3D printed materials and flexible materials, electronics, we need at least to be able to manufacture metal patterns on them. And to do so, we have a good number of options. Probably the most well-studied and versatile approach is inkjet printing, which has a very good number of good features. However, inks are made of nanoparticles, which are dispersed in binders and solvents. So at a certain point, we need a thermal curing or a laser curing, and not all materials or applications can withstand that. Additionally, the adhesion between inks and the substrates depends a lot on the wettability of the substrate and on its surface energy and so forth. So the point is inkjet printing is not always a viable solution. For these reasons, this paper focuses on alternative imaging approaches to perform selective metallization at room temperature. This way, we can perform this metal pattern also on materials such as bioplastics, which are very temperature sensitive materials. I report here a couple of examples. One is copper adhesive foil, which is basically a metal pattern transfer technique. In this technique, we start from copper adhesive foil, where we basically create the metal pattern that we want using, for instance, photolithography, like I reported here, but also we can use laser cutting or similar stuff. And then we transfer this metal pattern on the material of interest. And of course, this is not actually additive manufacturing because we have to remove the copper that is unwanted, but it is compatible, for instance, with the roll-to-roll manufacturing. This approach can be used on a great variety of materials. And what's more, the traces are actually made of bulk copper, meaning that we can achieve a very high conductivity and we can actually solder components on these tracks. Another technique that I wanted to show you is this embossed surface technique, which is really, at its infancy, but basically it uses 3D printing not only to create the electric substrate, but also to identify the areas to be metallized, which are 3D printed in relief with respect to the rest of the surface. This way, basically, we can apply conductive paste with very simple tools, such as a brush or a swab or a roll. And this conductive paste can be, for instance, colloidal silver, which dries at room temperature. And therefore, of course, the quality of the metal trays is dependent on the tools that we're using and on the resolution and accuracy of the 3D printing process. However, we feel that this approach has the potential to be a very low-cost approach for IoT electronics, because in the end we only need one tool, the 3D printer, to make the component. And here, as an example, I reported microstrip crossover. You can see it here at the bottom. And it is manufactured using a low-cost FDM printer. The white material is polylactic acid, which is a bioplastic, while the metal traces are manufactured using colloidal silver. As I mentioned, there are many other different techniques, and if you are curious or interested, please have a look at the paper. I want to conclude this very short overview by showing you a couple of examples of complete wireless sensors manufactured with this approach. One of them is this wireless pressure sensor manufactured combining stereolithography with embossed surface technique. The transducer is the one circled in light blue, and it is a 3D directional coupler where the direct port is connected to an horizontally polarized antenna, while the coupled port is connected to a vertically polarized antenna. And basically, when we apply a pressure, we are changing the coupling coefficient of this directional coupler. So we are basically changing the power ratio of the signals transmitted with the two antennas. And if we measure the power received in these two orthogonal channels, we can retrieve the pressure information. Another transducer here that I'm reporting is a force sensor. It is manufactured on PHBV, which is again a bioplastic, using the copper adhesive foil approach. Here, the sensing element is circled in red. It's a kind of switch, and it is manufactured using a metal pad. And then we have a 3D printed grid based on peptide functionalized silk fibers, which shows viscoelastic behavior. And then we put on top of it another metal pad, which is connected to ground. So basically, usually this 3D printed grid keep these two metal pads separated. So this switch is off. But when you apply a force above a certain threshold, basically this 3D printed grid reflows. And so the metal pads touches each other, and this means that the switch is closed, and we can see a burst in the power transmitted by the sensor. The last example that I'm reporting is a crack sensor, which is manufactured on the cardboard using this copper adhesive foil approach. The circuit is in microstrip technology, and here we avoid using NEVs to basically ease the disassembly of the different materials at the end of the life cycle of the sensor. In fact, the copper is attached to the cardboard only using glue, so we can easily peel the copper off cardboard. And then we can also remove the surface mount components using hot air. So as you can see here on the right, with a couple of steps, we could basically separate all the components of the sensor, and the surface mount components can be reused. We actually did it in the lab, and while the cardboard and copper can be recycled. In the paper, we also showed many other different sensing approaches. Also, this is a review from other research labs, and we also discussed a bit the performance and the frequency limits of these technologies. And so if you are interested, please have a look at it. Thank you very much for your attention.